Okay, this is a technical session number 4, and we have 4 great papers on performance optimization. Our first speaker is Gyuyeong Kim. Gyuyeong is an assistant professor in computer science at the Samsung Women's University, South Korea. His research interests are computer networking and systems. So today he will present his work, NetClone, fast, scalable, and dynamic request cloning for microsecond-scale RPCs.
Thank you for the introduction. Hi, everyone. I'm Gyuyeong from Samsung Women's University. So today I'll be talking about my work, NetClone, a fast, scalable, and dynamic request cloning for microsecond-scale RPCs. So modern online services consist of various microservice components, and these components interact via RPCs. So one recent trend is that the RPC is getting smaller and shorter. So the services require microsecond-scale tail latency for better user experience. Unfortunately, RPC requests may experience unexpected latency variability. However, this is hard to eliminate because the sources are very diverse. So although we cannot eliminate this variability, but we can mask this variability. So request cloning, also known as redundancy, is a simple and powerful technique to mask variability. So the idea is very simple. Well, in a client-based cloning, the client duplicates the request to different servers and takes the faster response. However, while it is simple, but it always clones the request, so it doubles the system load. So a key drawback is it is only beneficial within a sweet spot. So in the below figure, you can see that the throughput is very limited, while there is some latency improvement within a sweet spot. So to resolve this, recently, RAG, a coordinator-based approach, is proposed. So in RAG, instead of a client, the coordinator node performs dynamic request cloning. So the RAG coordinator replicates the request only if there are 2 idle servers. So there is no sweet spot. However, this is not enough to serve a microsecond-scale workload. Well, there are 2 reasons for this. The first reason is that in the age of microseconds, a few small microsecond-scale overhead can increase total latency excessively. So you can see that the portion of cloning overhead caused by the coordinator is large if the runtime of RPC is small. And the second reason is that the coordinator node is a commodity CPU with a commodity server that uses CPU, and the CPU has the limited packet processing performance. So if we want to provide support multiple servers, then we should provide multiple coordinators as well. So, however, this incurs additional cost to build and maintain a tier of coordinators. So then, how can we perform dynamic request cloning quickly at scale? Well, our approach is NetClone, a switch-based dynamic request cloning. So you can see that in the right side figure, there is a programmable switch between clients and servers. Then why in-network request cloning? Well, the network switch is a vantage point for dynamic request cloning because the network switch provides high performance. The switch can process a few billion packets per second, and it can process a single packet within 100 of nanoseconds. And also, thanks to the recent emerging programmable switch ASICs like Intel Topino, we can customize the switch data plane in PIFO language. So by using the network switch for request cloning, we can achieve this requirement easily. However, switch hardware is not for computing but for packet forwarding, so we should address several technical challenges to realize the idea. So in this work, we carefully designed our custom data frame by addressing several technical challenges to satisfy the strict resource constraint. So this is the overview of a NetClone architecture. So we have 3 key modules in the switch data frame. The first module, request cloning module, which clones the request only if the two random servers are idle. And the second module, a response filtering module, is designed to reduce client-side overhead. So the slower response of a request is unnecessary to the client. So if the switch can filter out the slower response, we can avoid the performance degradation caused by the redundant response. And next, the state tracking module, namely keeps track server states in the switch because the switch and servers are different nodes in the network. And we also use a custom header field to support the NetClone functionality. So now I explain how the switch handles requests. So upon receiving a request, the switch picks two candidate servers, say server 1 and server 2, and update the destination IP address to server 1. And next, the switch checks the states of server 1 and server 2 sequentially. So here we use the shadow table, or copy of the state table. The reason why we use the shadow table here is in the current PISA architecture, we cannot access the same register within a single path. So, and next, if there is any busy server, then the switch does not clone the request, and the switch just forwards the request as usual. However, if both servers are idle, then the switch clones the request. Specifically, the switch forwarded the original request to server 1, and for cloned request, the switch recirculated the cloned request. This is because we cannot update the IP address of the cloned request at the time of cloning. So we make the cloned request revisit the ingress pipeline by recirculation. So after updating the destination IP address to the clone, the switch can forward the cloned request to server 2. So now the switch, upon receiving a response packet, the switch first updates server state. So as we make server piggyback the server state in response packet, so the switch first updates server state, and next, the switch checks the filter table. So filter table is to identify the arriving response is a faster response or slower response. So if there is no matched ID, that it means that the arriving response is the faster response of the request. So the switch puts a request ID into the filter table and forward the response to the client. However, if there is a matched ID, then the switch simply drops the response because the faster response of the request have already visited the switch. So to evaluate the NetClone, we have implemented a NetClone prototype using Intel Topino, and we have built a test bed with a single Intel Topino switch and 8 commodity servers. So for workloads, we use a synthetic workload with dummy RPCs, and also we use key value stores with skewed access patterns. So this is the main result. Then we can see that NetClone is the only solution that provides low tail latency and high throughput at the same time. And in this experiment, we compare NetClone against the RAG. So RAG shows the worst performance between compared schemes. So the one notable point here is that there is a latency gap even at low loads between RAG and NetClone. This is because the RAG coordinator incurs additional latency overhead for request cloning. So this is the result with the Redis key value store. So this result demonstrates that NetClone can improve the performance of real applications as well. And this result shows that our response filtering module is especially effective at high loads where too many duplicate response occurs. So the module is effective to reduce client-side overhead. So conclusion, microsecond-scale RPC require microsecond-scale tail latency. So NetClone is a dynamic request cloning mechanism that provides leverage programmable switches. A high-level key takeaway of this work is programmable switches can play an important role in the age of microseconds. So this is the end of my presentation. Thank you, and feel free to ask any question. Thank you.
Yeah, question from the audience.
Hello, this is Jiaxing Lin from UT Austin. Thank you for the talk, very interesting work. I'm wondering, do you have to make any modification to the end-host transport layer to support request cloning in the programmable switch?
Okay, that's a good question. Well, we did not, NetClone does not require modification in transport layer protocols, but by default, NetClone uses a UDP. So the answer is that NetClone does not modify transport layer protocols.
Oh, yeah. So can you talk a little bit, like, if the end host is using TCP or RDMA, like, what would be the possible way of supporting the cloning? For example, can you do some very fancy thing in the programmable switch to support?
Oh, yeah. Okay. So to use TCP, well, the motivation of this work is that the RPC is getting shorter and smaller. So it is very small, so that a request is a single packet request. But some RPC framework may use TCP. So to support the TCP, well, first we append some dummy payload that consists of only a NetClone header, because the TCP we needed to establish the connection before communication. And to support the RDMA, well, actually, supporting RDMA is our ongoing work, because, well, and I think that there is several issues to use NetClone with the RDMA-based framework.
Okay, thank you.
Yeah, one more question. Yeah, here.
Hi, Sakatre from Meta. So because you're looking at almost nanosecond level performance, right? So how can you know which server is idle at that time scale? Because it can also change very, very quickly, right? Whether it's idle or not. And if you anyway can somehow detect it, can't the client itself detect it and actually make the thing instead of changing the switch in between?
Oh, your question is that there is some time gap between the reported server state in the switch and the actual server state, right?
Correct. If it changes, in the order of scale of nanoseconds or even microseconds for that matter, it's very hard to exactly know what will the state when the request will land there. And if you make the assumption it's known somehow, then why can't the client also know that and actually send multiple requests if needed?
Well, I'm not sure I can correctly understand your question, but the switch can process a single packet within a nanosecond scale, and if when the switch duplicates the request, but the actual server state is not idle, busy, then we make the server just drop the cloned request, so to avoid some throughput degradation.
Okay, so why can't
due to the time constraint, we are gonna take this question offline. Yeah. Okay. Yeah, let's thank the speaker again.
Thank you.
Our next speaker is Ruyi Yao. Ruyi is pursuing her PhD degree at Fudan University. Her current research interests include software-defined networking and programmable data plane. So today, she will present a BM-W3, large-scale, high-throughput, and modular PIFO implementation using balanced multi-way sorting tree. Yeah, welcome.
Good afternoon, everyone. My name is Ruyi Yao, and I'm from Fudan University. Today, I'm glad to share our paper entitled BM-W3 here, which is about implementing a large-scale, high-throughput, and a modular programmable packet scheduler. This is a joint work with the Pengcheng Laboratory and New York University. Packets from different flows will contend for the output link, and the scheduler will decide which packet to transfer. A lot of scheduling algorithms have been proposed for different application goals. However, few of these algorithms have been put into use on chips due to high hardware cost. So it's indispensable to build a programmable packet scheduler to enable them. Pushing first out, or PIFO in short, is the most popular model in recent years to realize the programmable packet scheduling. In the PIFO model, each packet is tagged with a rank by the rank function. By changing the rank function, different scheduling algorithms can be implemented. The head packets of flows are stored in a priority queue with ascending ranks in the PIFO model, and the packet with the smallest rank goes first. Modern networks demand low time and space complexity on programmable schedulers. For one thing, the number of flows in the data center is growing explosively thanks to virtualization, so programmable packet schedulers are expected to be scalable enough to isolate and pace a larger number of flows. For another thing, with increasing linking speeds, the time budget to make a decision for scheduling is getting smaller, and the time-sensitive applications require nanosecond precision. So programmable packet schedulers are expected to have large scale, have a high throughput. In short, modern networks need a large scale and high throughput programmable packet scheduler. There are many hardware designs for the programmable schedulers already. Heap-based implementation utilizes SRAM to store packets. It has large scale. However, pheap has vested idle cycles, and pipeline heap features complex hardware designs. Register-only implementation has a high throughput, but suffers from small scale, which can support no more than 1,000 flows. FIFO-based approximation uses FIFOs to implement the PIFO, which sacrifices the accuracy in exchange for the large scale and high throughput. None of them combine accuracy, large scale, and high throughput. So we propose the BMW tree, balanced multi-way sorting tree, to build an accurate, large scale, and high throughput programmable packet scheduler. Our work consists of one data structure and two hardware designs. First, I will introduce the data structure. In an M-order BMW tree, each node contains up to M unsorted elements. Each element represents a packet, which carries the packet rank value and the counter. The packet's metadata is omitted for brevity. The heap property is satisfied in the BMW tree. Here we show a 4-order BMW tree with 2 levels. Subtrees are distinguished by different colors, and the counter records the total number of elements in each subtree. Now let's see the push operation. Elements are always inserted into the leftmost least loaded subtree, and the counter will be increased by 1. Suppose there is a push 17 operation. The 4th subtree is chosen, and 17 will kick 29 down to the 2nd level to satisfy the heap property. Then 29 will find an empty slot in the 2nd subtree and occupies it. All elements find their place and the push operation finishes. As for the pop operation, BMW tree always pops the smallest value in the root node, and the counter is decremented by 1. 10 is the smallest, so it's popped out. The smallest element in each subtree is lifted from the 2nd level to fill the vacant position. The heap property is satisfied and the pop operation finishes. BMW tree has the following properties. First, it's modularized. Modularization simplifies the implementation and test. Secondly, it has insertion balance, which means each insertion can make the tree more balanced. The balanced structure makes BMW tree consume less power. BMW tree is also pipeline friendly with autonomous nodes. Operations on each node are independent of the rest of the tree. Thanks to these properties, the hardware frequency of BMW tree is independent of the tree depth in theory. One of the hardware designs is based on registers. We call it RBMW for short. RBMW is modularized, and each node only connects the parent and children node. The details about its building block can be found in the paper. With the pipeline, RBMW can deal with the consecutive push and pop operations every 2 cycles. Despite its high throughput, its capacity is limited by the register resources. To reduce the register usage, we propose ranking processing unit-driven BMW tree, RPU BMW for short. Considering the BMW tree is modularized and the nodes are autonomous, we design a ranking processing unit to complete the computing tasks of all nodes and store all nodes in an SRAM. Nodes are dynamically loaded into or off RPU. For the push 17 operation, node 1 and node 5 are operated by the RPU in turn. This design achieves large scale, but the throughput is low. During the push and pop operation, we noticed that at any time there is only one active node in each level, so we can set one RPU for each level of the tree, and nodes on the same level share the RPU of its level. Data from different levels interact through the RPU array, and multiple RPUs run in a pipeline. We show how to process push and pop operations in pipeline in a 2-level RPU BMW tree. More details about it can be found in the paper. RPU BMW is also modularized, and RPU only connects its predecessor and successor. With the pipeline, RPU BMW can deal with the consecutive push and pop operations every 3 cycles. As the capacity of RPU BMW grows exponentially with the level, only a few RPUs are needed for large scale. So this design achieves the high throughput and the large scale. The prototype of RBMW and RPU BMW is written in Verilog and implemented on XCU200 FPGA. We also synthesize RPU BMW in GlobalFoundries 28nm process. The results show the frequency and the resource consumption of RBMW with a different order on FPGA. It shows that RBMW can support as many as 5,000 flows. With the same capacity, the 2-order BMW's throughput is 4.8 times that of PIFO. As for the RPU BMW, it can scale to 87,000 flows. With a similar capacity, the frequency of 2-order RPU BMW can be up to 5 times that of PIFO. In the 28nm process, the frequency of RPU BMW can be as fast as 600 MHz, reaching a scheduling rate of 200 million packets per second. RPU BMW supporting 37,000 flows has an even smaller area than a 1,000 PIFO. To conclude, we propose a novel data structure, balanced multi-way sorting tree, and build 2 hardware designs based on it, RBMW and RPU BMW. RPU BMW is the first accurate PIFO implementation, supporting over 80,000 flows at as fast as 200 million packets per second. That's all. I'd like to take any questions.
Yeah. Any question from the audience?
Psychotherapy from Meta. In your picture, what happens if all the nodes in the second layer is also already full? Do you go into the third layer? So is it like a log m or log n complexity of the push?
Sorry, can you repeat your question?
Sorry. If you go back to the picture you had, you were showing there is space in the second layer where you push the object in the push, right? In the the actual picture of that your tree. Yeah. No, even this will work. Yeah, this is good. go to, it doesn't matter. So if you see, when you push a new one, the second layer already has space. My question was, what if it does not have any space? Do you go to the third layer? Or in that case, it's a log n complexity of push?
Yes, that's right. Your understanding is correct.
Okay, sounds good. So, let's thank our speaker again. Yeah, our third talk will be given by Ruyi. Ruyi is a second-year PhD student in computer science at Peking University, advised by Qun Huang. His research interests include network measurement, network performance analysis, and programmable networks. He will present BitSense, universal and nearly zero-error optimization for sketch counters with compressive sensing. Yeah.
Hi, my name is Ruyi, and I present BitSense, universal and nearly zero-error optimization for sketch counters with compressive sensing, which I worked on with Yang, Xiang Chen, and my professor, Qun Huang, at Peking University. Measurement is crucial to network management. With the support of modern programmable switches, sketch-based network measurement has become popular. It deploys sketches on programmable switches and measures predefined flow statistics. The control plane then periodically collects this sketch and reports them to management tasks. Here is a generic view of the sketch. It consists of arrays of fixed-size counters. Moreover, it supports at least two operations. The first is updating with a packet. In measurement jargon, a packet is represented as a flow key plus a packet value, whose definition can be application-specific. The update operation hashes the flow key to select counters and adds the packet value to these counters. The second operation is querying a flow statistics. It hashes the flow key to multiple counters and combines their values to yield an estimate. The strengths of the sketch are twofold. First, it achieves high accuracy in limited memory space. Second, it incurs low computation and access overheads. However, on-chip memory becomes a bottleneck for sketch deployment nowadays. There are three causes. First, high-speed switches have limited RAM due to power and speed constraints. Second, rapid traffic growth requires more sketch counters to maintain accuracy. Third, collocated functions also consume more and more memory, so the memory budget for a single sketch is extremely tight. In answer to the memory bottleneck, we focus on the counter compression. The motivation is that sketch counters contain implicit waste, which is justified by two observations. First, counters must have enough bit to avoid overflow. For example, if a value exceeds 2 to the 8th power after update, an 8-bit counter overflows to 0 and induces a large error when queried. So 16 bits are required in this scenario. Second, most counters have small values and do not need higher bits. To illustrate, we test the counter distribution on multiple sketches. It is always skewed towards 0 due to traffic skewness and hash conflicts. Previous research proposes two methods. The first is to adopt variable length counters. Specifically, it begins with short counters and merges them on demand to hold larger values. However, it incurs formidable addressing overhead, and it is not universal, since merging can break the data structure of some sketches. The second method is by counter sharing. Specifically, parts of the counter share a common physical address. It uses unbiased estimates or message passing mechanism to restore the full counters. However, this method incurs severe accuracy drop due to lossy compression. Now we introduce our work, BitSense, whose primary features include memory efficiency, universality, nearly zero error, robustness, and user-friendliness. The architecture of BitSense is as follows. It consists of 4 steps. Step 1 is that users develop sketches with the BitSense counter interface. The interface abstracts the update and query operations, and users feel that they are just manipulating fixed-size counters. Step 2 is that BitSense compresses the sketch to reduce implicit waste. It consumes far more memory than before at a low overhead. Step 3 is that packet updates the transform sketch via the interface, which ensures the same semantics as before. The last step is that the control plane decompresses the transform sketch for query. It produces a restore sketch that is isomorphic to the raw sketch. Moreover, it provides a nearly zero error guarantee. So let us focus on the idea of compression. Specifically, BitSense represents a sketch counter using shorter segments. Here is an example of representing a 24-bit counter with 3 8-bit segments. Now that each segment holds the overflow value of a lower segment, we can organize these segments into different layers. Recall that counter distribution is skewed, so higher segments are sparse. This is important. Now we design a hash-based compression scheme. Specifically, we reduce the number of segments in higher layers. For example, instead of 6 layer 1 segments, we can only use 3 segments. Accordingly, we add the overflow to multiple higher layer segments selected by hash functions. The hash function hashes the index of the overflow segment to a higher layer index. Here we show an example using 2 hash functions highlighted in different colors. So how do we decompress these segments with minimal error? The answer is by formulating a constraint optimization problem. It has 4 ingredients. First, a priori knowledge is sparsity, which suggests us to find sparse solutions. Second, the constraint is imposed by hash maps. We must find solutions subject to the constraint. Third, the input is segment values of a higher layer. And finally, the output is the restore segments of the current layer. 2 ingredients are crucial to ensure nearly zero error decompression. The first is a compressive sensing-based optimization goal that favors sparse vectors. And the second is 1-bit markers that indicate non-overflow segments. It helps to shrink the solution space. Moreover, we proved the nearly zero error property in theory. The key result is as follows. As long as the number of higher layer segments is 1.09 times that of the actual overflows, decompression achieves zero error with high probability. For example, suppose there are 10,000 segments and 10% of them overflow. Then the next layer only needs 1,090 segments to attain nearly zero error decompression. There are other designs to enhance BitSense, but due to the time limits, we only give a short list here and invite you to read the paper. First, BitSense supports real-time counter estimation by a lightweight auxiliary sketch. It also supports complex counter operations by composing basic interfaces. Moreover, it has P4 architectural support thanks to acyclic dependencies. And finally, it has an efficient auto-configuration scheme based on tight threshold results. Our results show that BitSense achieves low overhead and high accuracy. First, we show the resource usage measured on a Tofino switch, where only 9 megabytes of RAM are available for sketch algorithms. We use 3 testbed sketches, namely CountMe, SketchLearn, and Unimon. We compare the resource usage with and without BitSense and the difference for each sketch. Here is the results. We find that SRAM is a major resource bottleneck, and BitSense reduces by at least 10 to 4%. It saves even more memory given a larger sketch size. Meanwhile, BitSense incurs low overhead on other resources like memory access, pipeline stages, action numbers, hash computation, and so on. The next result shows that BitSense improves the performance of existing sketches. Here we test the accuracy of flow size estimation. Our workload is a mixture of a Akeda trace and a data center trace. Following the convention, we use ARE and flow ratio as our metrics. A lower ARE and a higher flow ratio indicate better accuracy. From the results, we obtain 2 findings. First, BitSense attains the same accuracy level with 25 to 50% less memory. Second, given the same memory budget, BitSense reduces error by orders of magnitude. Besides, the evaluation on other measurement tasks demonstrates the same conclusion. More results can be found in the paper. It includes the result on robustness, optimality, recovery time, overhead, and micro benchmark. Now, to recap, we first identify and quantify the amount of implicit waste in sketch counters. Motivated by the implicit waste, we designed the BitSense architecture with universal and user-friendly interfaces. Next, backed by the theoretical and experimental results, the compression scheme achieves nearly zero error. Finally, we present a Tofino implementation and perform a thorough evaluation to show that BitSense achieves high accuracy with limited overhead. And thank you for your listening, and I'm happy to take any questions.
Any questions from the audience? Okay, I'll ask a question.
Okay.
So I think in your big diagram, you show a control plane that needs to do analysis on the telemetry data. Let's think about you have a end-to-end application that will leverage this telemetry you are collecting. For that type of end-to-end application, does it need to spend extra, for example, CPU cycles to use your new sketch system?
Oh, well, it depends, because our system is targeting at programmable switches. It's not at end host. So the switch CPU, I presume what you meant.
Yeah, it's the control plane that.
Yeah, the switch CPU of the switch OS. Yeah. Okay. So it does take extra cycles to for the control plane to decompress the compressed sketch. So it can cause extra latency. But the advantage of BitSense is that we also provide a real-time data plan counter estimation interface so that you can directly estimate the current value of a counter just in data plan. And no decompression is involved in that method. Yeah. Yeah.
Okay.
Eddie Kohler, Harvard. Would you use this structure on an end host? What would you change if you wanted to use it somewhere other than? What is P4 and Tofino centric, and what is not?
Okay. The memory bottleneck is particularly. We designed this. We designed the BitSense for programmable switches, and the reason why it can support this architecture. Oh, sorry. Due to time limit, I didn't present the details here. But the gist is that the implementation of all the BitSense interfaces has no cyclic interface, and we can efficiently use the SRAM and state for ALU in just one pass to support all the interfaces on programmable switches. Yeah. I hope that answers your question. Yeah.
Okay, great. Let's thank the speaker again. Okay, let's move to the last talk of this session. The presenter is Guangda Sun. Guangda is a fourth-year PhD student at the National University of Singapore, advised by Professor Jialing. And he has been working on distributed and fault-tolerant systems. So today he will present NeoBFT, accelerating Byzantine fault tolerance using authenticated in-network ordering.
Thank you. Hello, everyone. Today I'm going to talk about NeoBFT, accelerating Byzantine fault tolerance using authenticated in-network ordering. This work is completed with Mingliang Jiang, Xinzhe Kui, Yunfan Li, and Jialin Li from National University of Singapore. Permission blockchain has gained popularity recently. Participants without mutual trust to each other use permission blockchain to keep consensus, for example, in trading, online payment, and supply chain management. These use cases demand both high throughput and low latency, which cause the permission blockchain usually deploy in data centers for low and predictable network latency. The deployment of permission blockchain must fulfill a series of challenging requirements. Permission blockchain must tolerate adversarial participants and provide strong consistency. And these are achieved by using BFT, or Byzantine fault tolerance replication protocol among participants. At the same time, permission blockchain also demands scalability and high performance. Can BFT protocols provide the desired performance? Unfortunately, existing BFT protocols cannot. In this figure, we can see the throughput and latency characteristics of various previous BFT protocols. The desired performance of permission blockchains, which is high throughput and low latency, cannot be achieved at the same time by any of these protocols. We noticed that prior solutions only consider protocol optimizations and trusted components on end hosts, and we shall ask that whether we have any other design dimensions to explore. In-network ordering has been developed in data center networks recently. It introduces a stronger network model that provides ordering guarantee. It is implemented using network programmability and incurs near zero cost, which enable us to co-design distributed protocols with performance benefits. It has been applied to a wide range of distributed systems, such as NoPaxels, Aries, and Hydra. With in-network ordering, there is a programmable switch that forwards all client messages and serves as the sequencer. When clients sending messages, they first arrive the sequencer switch, and the sequencer assigns each message with a sequence number based on their arriving order. Then the sequencer broadcasts client messages to replicas. When replica receive the messages, they deliver the messages to application in the order of messages sequence numbers. So the messages are always delivered to every replica in the same order. So the question is, can we apply in-network ordering to accelerate BFT protocols? In this work, we propose a new approach to improving BFT performance in data centers by offloading ordering guarantee to the network. We designed a new network primitive called Authenticated order multicast, which can provide in-network ordering to BFT protocols. And we co-designed a coordination-free BFT protocol called NeoBFT. And finally, get BFT with both high throughput and low latency. Next, let's move on to AOM design and implementation. Naively applying in-network ordering into Byzantine fault model will not work because adversaries can impersonate network sequencer and generate conflicting message order. For example, let's say sequencer's messages do not reach some replica because of network partitioning. In such case, if there's any faulty replica who relabel the received messages with different sequence numbers and broadcast the messages can be received by the partitioned replicas. Then the replicas cannot reach consensus on the message ordering and fail to maintain consistency. To solve this problem, we need to find a way to let replicas determine the correct message order, and the answer is authentication. Our solution is to let sequencer switch to sign the messages and replicas to independently verify message signatures to make sure that messages are indeed generated by sequencer. We designed a new network primitive called Authenticated Order Multicast, or AOM, which augment prior network primitives to provide in-network ordering for BFT protocols. It has similar properties to prior primitives like ordered, unreliable, and drop detection. But for the first time, in-network ordering can provide authentication and transferable authentication properties. Let's see what's happening to the previous example when we have AOM. When clients send message with AOM, besides assigning sequence numbers, sequencer also signs each message with a signature, then multicast to the replicas. The replicas can verify the signatures, know that the messages are indeed from the sequencer, and accept the messages. And if there is any faulty replica trying to publish its own ordering to the other replicas, the message will not be accepted because the faulty replica cannot generate a correct signature for the message. In conclusion, now replicas can determine the correct ordering by sequencer with authentication. Authentication can solve our problem, and the next question is how to implement it in network. Implementing authentication requires cryptographic algorithms, which may contain complex computation, involve large prime numbers, and have unbounded loops and large vectors. It's hard for programmable data plan to deal with this due to hardware limitation. So to make the cryptography feasible on programmable switch, we choose to deploy a lightweight message authentication code, or MAC. The implementation uses two pipelines of a programmable switch. Pipeline 0 is for sequencing and multicast, and pipeline 1 deploys 4 parallel MAC generation instances. Messages first get sequenced in pipeline 0, then recirculate in pipeline 1 until 4 MACs are generated. Then they go back to pipeline 0 and multicast. The problem with MAC vector is poor scalability because it requires 1 MAC per receiver. Public key cryptography, on the other hand, offers infinite scalability, but it is too complex to implement directly in the switch data plan. So we propose a new switch architecture that integrates a cryptographic coprocessor, and we implemented it with FPGA in our prototype. In our prototype, we implement SECP256K1 signature generation on FPGA, and switch is used to assign sequence number and multicast. Both implementations provide desired authentication, and they are efficient enough to support AOM-based replication protocol, which we are going to talk about next, the NeoBFT protocol. Same as the standard BFT setup, the NeoBFT protocol needs 3 F+1 total replicas to tolerate F Byzantine 40 replicas. At the same time, it leverages the guarantees of AOM to realize single RTT commitment in normal operation, which I will show later. It also has efficient protocols to handle network anomalies and the will change protocol for leader and switch failover. In normal operation, clients send requests to replicas with AOM. Replica verifies the AOM message, speculatively execute the request, and reply to the client. Client can confirm the execution is durable after receiving replies from 2 F+1 replicas and commit. As a result, client commit in single RTT. There's no coordination among replicas, and the protocol can tolerate F40 replicas. There's more details in the paper that I have now talked about. Please check the paper if you are interested. Lastly, the evaluation. We perform a series of evaluations to compare NeoBFT with 4 previous BFT protocols: PBFT, HotStuff, ZZiba, and MinBFT. Our evaluations shows NeoBFT has best performance and good scalability, and it is also resilient to network anomalies. The result of performance evaluation is shown in this throughput latency graph. As we can see, NeoBFT achieves desired high throughput and low latency. Compared to other protocols, NeoBFT shows 1.8 times to 3.1 times throughput improvement and 8.5 times to 42 times latency improvement. Furthermore, NeoBFT still has better performance when the network is adversarial. Please check more evaluation results in the paper. In summary, we propose a new approach to accelerating BFT protocols in data center by offloading BFT ordering guarantees into the network. We design and implement in-network authentication to tolerate adversarial behaviors, and we co-design new BFT replication protocol, which shows significant throughput and latency improvement over existing protocols. That's all for my presentation. Thanks for listening.
Question from the audience? Okay, I'll ask a question. So, for example, for the comparison points like hot stuff, it may the region it may consider is a high F. Mm-hmm. So I'm wondering, like, in terms of this scalability, in terms of F, like, what will be the performance behavior of your BFT protocol compared to, for example, a hot stuff?
That's a very good question. So one of the main concerns of scalability of NeoBFT actually comes from the scalability of the network primitive, which is AOM. As I talked, we first developed the MAC variant of the AOM and realized that the scalability is not enough to support a large deployment of the protocol. So we actually offer the alternative public key cryptography which can theoretically support infinite scalability. Yeah, and as we show in the evaluation, which you can check in the paper, actually the scalability of public key cryptography is according to our expectation, and we have the evaluation that deploy up to 100 replicas with public key cryptography, and we noticed that the throughput drop is very acceptable. So yeah, I guess the NeoBFT has a very good scalability.
Okay, great. Thank you very much. Any other questions from the audience? Yeah.
Hi. I get a mic. Sorry. Yeah. My name is Si Zhe from Northeastern University. So I personally, I'm pretty interested in blockchain. So I wonder, so when it comes to signature and verification, how do you manage, like, how do you distribute the public key of the sequencer to other replicates? And how, like, if you want to change the key pair of the sequencer, then how do you update the public key to other?
Right.
Yeah.
Right. Thank you. Yeah, that's also a very good question. So actually, that is a part of the network reconfiguration service. So since we are actually targeting the scenario of permission blockchain, we can assuming that all of this sequencer and also the replicas, they are under a controlled network environment where a reconfiguration service and also a trusted credential exchange service can be applied to such case. So it's like not only when you want to change or update the public key, and also when the switch is failover and the new switch, the new sequencer, they may come into the system with a new public key, and how do the replicas can be aware of that and ensure that the old and the new public key, these sequencers, they do not cause any accident of the consistency. So we have the failover protocol on the replica that is specially designed that this it's similar to a wheel change, but it's specially cared about the old and the new sequencers, and these public keys that when they are sent by the reconfiguration service, everyone will keep synchronized on this information.
Thank you. Thank you.
All right, let's thank the speaker again.
Thank you.
Now let's move to our mini panel. So let's welcome in the session. Okay, now is an opportunity for the audience to ask more questions, or if you have questions among yourself.
Hi, thank you. So I have a question to our last speaker. So I'm Shushavan from Rice. So I was thinking that you have one slide, right, where you are using some kind of FPGAs to kind of generate the signatures and stuff, right? So do you have any idea how this would impact your cost of your architecture, right? Because you have shown that this can achieve performance, but how much excess cost you need to get that at scale?
Sorry, can you repeat the last part? Is the generating signature on FPGA and what?
Yeah, so then I am kind of thinking that, so you need some kind of extra like hardwares, right? To kind of have some things. So at scale, whenever you are trying to deploy this architecture, how much extra cost that will actually incur? So that was my question.
Okay, so the question is, if this is actually coming to the deployment, how will be the architecture of the network programmable switch?
Yeah, right. How much like extra cost you need? For example, if you have to deploy FPGAs or like all over.
So our main expectation is that in the future there will be a programmable switch that has specialized cryptography accelerated embedded, so that everything we must manually program and compiled on FPGA can be some kind of hardware into the programmable switch. So we argue that if this AOM is going to be practical, then doing such cryptography operation on in our computation could be a must-have need. If that is the case, then yeah. So we really expect that future programmable switch can have such functionality that actually support non-trivial cryptography out of the box and make this kind of the thing that actually can happen in the commercial networks.
I will ask him, I think sketch-based algorithms have strong mathematical characteristics. So can you know in advance how much your general structure can improve the performance of the sketch-based algorithm?
Oh, okay, yeah, that's a good question. And of course, you can know it at the deployment time, because once you deploy the structure onto the programmable switch, it is fixed, and reconfiguration is time-consuming. And so the central question is that how can we know in advance that how much implicit waste there is? Yeah. So the answer in the paper is that it is defined by two major factors. One is the sketch structure itself, and second is the anticipated flow pattern. So once you know these two factors, you can do empirical engineering stuff to find how many implicit ways there are by finding the counter distribution. And from that distribution, you can properly set all the configuration parameters by the auto configuration scheme provided by the BitSense itself, so that you can eliminate implicit ways to the greatest extent while keeping nearly zero error guarantee. Yeah.
Thank you.
Okay. Maybe let me ask a question that involves all the four speakers' talk. So as all your papers point out, we have limited resource on programmable data plane, and you are all inventing new method to use that resources. Like imagine your work are combined together on some programmable data plane. Like how do you think the resource is gonna be shared or used if we want to use it for transmitting RPC, network monitoring, and network ordering, all these things together? Yeah, I don't know whether you have any thoughts on this question.
I think this is a good question, and personally, I think it's challenging to achieve all these goals or implement all these functionalities on just one switch. So a sensible approach may be to use network-wide coordination, because that you can combine resources and capacities of multiple programmable switches all over the network. And it's a and maybe by this method, you can achieve better scalability and implement complex functions. Yeah. Okay, so any other ideas?
Okay, great, thanks. Any other? Okay, I think we can end it here. And so our next session is the best of CCR. So we'll have a break of maybe 5 minutes, yeah.